through this real quickly. I did notice that someone, when they went through and did this, drew on, that red hydrogen, and then couldn't quite tell what was happening. They started to add arrows, doing something like this, because they started to make the assumption that that red hydrogen was the black hydrogen, which is patently false. Those are different hydrogens. Okay? That red hydrogen is drawn on there, which is good to accent the fact that hydrogen is there. It is still present. Didn't change in the whole course of the reaction. It's still in that location. Why was the black hydrogen added on? Because what happened in the next step?
A hydride shift.
You ended up getting a hydride shift. Irritatingly enough, where did that black hydrogen go in the new drawing?
Next to the red hydrogen.
It wasn't drawn on there. Why was it not drawn on there? Because we can imply hydrogens. That step tends to be one of the trickiest steps for students to deal with, particularly when it centers on hydrogens, is that what we've done is a shift. Right? And we could reference it as a 1-2 shift. We took our black, I meant to draw that as black, oh well. It's now purple. We took a hydrogen from the 1 position and we moved it to the 2 position, the carbon immediately next to it. You might say, well, neither of those are position 1 and 2. And you would be absolutely legitimately correct. That doesn't change the fact that when we look at that type of reaction, we number it based off of the atoms involved in the steps. The hydrogen is located at an arbitrary position 1, a starting position, and it moves to its ending position. Its ending position is 1 position away from it, so that becomes carbon 2. Right? So we could reference this as a 1-2 hydride shift. I would argue where I wanted you to go with it was be a little bit less specific and just call it a rearrangement. Okay? The next part, I know we're starting in the middle of this. What would be our mechanistic arrow to shift between those two? Okay? So I got a hand and I got a questionable face. So 2 things make me stop. Okay, we'll see the hand first.
Oh, I'm just curious. In a rearrangement, if it was like 2 away, would you do a 1 and 3? Okay.
Yep. So if I wanted that hydrogen to say move out to here, okay, that would be a 1-3 rearrangement. Typically, we don't see rearrangements that far away. Why? Why is it not likely?
It's a long way to go.
It's a long way to go. What is that hydrogen moving with? Okay, so one thought is it's moving with a positive charge. So I'm going to take this positive and I'm going to put it with that positive? No, what's moving?
The electrons.
The electrons with the hydrogen atom. So that hydrogen atom is taking the electrons and moving to this position. That arrow can get very, very confusing because that looks like a standard arrow. We're taking an atom and moving an atom. Curved arrows don't move atoms. What do they move? Electrons. Yet what is this arrow doing? Moving an atom. That's really confusing. So maybe what we should do, and I don't know if this is British or not, but I always blame the Brits for it, is invent a new arrow to represent this. This is a non-standard format, but it helps to represent this. Number 1, our arrow needs to start where the electrons are. Where are the electrons in that middle step? In the bond. So I want my arrow starting at that bond. Okay? I want those electrons to move to that atom, but at the same time, I want the hydrogen being dragged with it. By dropping a little curly Q in there, we can now accent the fact that, hey, this is not just a standard motion of electrons, this is moving with the atom. Okay? That is not how SmartWork will show it, because the curly Q is not a standard arrow. Okay? What it's attempting to show is accent the fact that we're doing something weird here. We need to be a little bit more careful when we draw out our results. Does that make sense? Okay. So we for sure addressed the 1-3. Jeanette? Okay. So we've now got probably the hardest curved arrow on this drawn. We've shown the full rearrangement. So now let's backtrack all the way out to the beginning. What happened there?
Formed a bond with the hydrogen.
So one option is to just go through and say, well, this is what happened. Okay? One of the things that's nice about mechanism arrows, okay, at least at this stage, is what you're being given is the reactant and the product. You just have to make sure the instructions to go from one place to the other make sense. Okay? Curved arrows are instructions. Okay? You have the beginning and the end. You just need to provide the instructions to get there. That's it. Okay? So if we go through and look at that beginning and end, what things changed across that reaction, that very first step? When I look at the beginning versus the end, what has changed? There's a hydrogen now attached to the oxygen. Okay? We'll deal with the positive charge in a second. And the reason why I would say we delay with the positive charge, when do we draw charges? Well, that's a really big question. I know. Work with it.
Once our structure is complete, then we do formal charge.
Once you've drawn a Lewis structure, you can then draw formal charge. Formal charge is the last thing that you do. Don't look at the charge and be like, oh, I'm going to start messing with the charge. Charges aren't doing anything. They can help accent the chemistry that needs to be going on, but the charge themselves is not doing anything. It has to be the electrons. So if we go to look at our structure, we have a new bond to a, whoops, that's an eraser, to a hydrogen. Because the only hydrogen I've got here that's reactive is that positive one, has exactly how many electrons?
0.
0 electrons. The oxygen must supply both. Okay? So I will start my arrow where there are electrons, and I will move them towards the hydrogen. Because the oxygen is supplying both electrons, I'm using the double-headed arrow. Each head of the arrow to represent a single electron. So a double-headed arrow is now the transfer of 2 electrons. That's the meaning behind those heads. Right? Once I've now done that, I could draw in the resulting structure. In that resulting structure, what happened to the oxygen?
It gained a positive charge.
I don't quite accept that it gained a positive charge. Being on the engineering path, you will probably be correct in your engineering classes, but in chemistry, we don't look at that.
It has to share an electron with hydrogen, so now
Right.
it's effectively lost.
It's
electron.
lost electrons. Okay? By losing electrons, we have thereby become
More positive.
positive. Okay? And the reason behind that specificity is that if you go through and start saying, well, the charges have moved, you start moving charges. Arrows don't move charges. Arrows move electrons. Okay? So it's trying to be very particular to use our methodology to show only one thing and one thing only. Okay? We've got that red hydrogen added on there because somebody else thought it was useful to include. Okay, so when we move to the next, actually before we do that, what step happened there in that first reaction? What did we do? What kind of mechanistic step?
Electrophilic addition.
Okay, so we could call it an electrophilic addition. Okay, you're saying electrophilic because we're adding a positively charged thing. Okay, and I'm going to challenge that, and electrophilic addition is fraught with all sorts of other issues. I'm going to challenge that right out of the gate because a hydrogen ion should not be called an electrophile. It should be called
One more thing.
an acid. H plus is an acid, not an electrophile. Okay? Definition-wise, does it match? Yes, but it's trying to be clear within the language to separate those categories so we don't get them confused and muddied. Okay? Carty disagrees with this, and he will reference the addition of a hydrogen as an electrophilic addition. I don't agree with that. Okay? It should be called an acid addition. Okay? But then the next part. So that's the electrophile term. So we can say borderline gray area, addition. What does it mean to do an addition? You take a pi bond and you add something to the pi bond. Do we have a pi bond? No. So it can't be any form of addition reaction because there's no pi bond. So electrophilic addition doesn't work. Okay? What have we done? We took an acid and we reacted it with something that got rid of the acid, which means we neutralized it. We did an acid-base reaction. This is purely an acid-base reaction. Okay? The other answer that I would accept would have been a heterolysis. Or not heterolysis, coordination. Okay? But acid-base is more specific to what is actually happening. And the next step, what happens? The oxygen bond breaks off. Nothing else happens to the structure. This is why having that extra hydrogen drawn on there can help us. Because if we don't have it drawn on there, what do we then start to think happened? Something happened to the hydrogen. Okay? But if we're familiar back in Unit 1, when we talked about the basic bonding structures for carbon, to have a carbon with a positive charge, how many bonds does it need to have? 3. Since there's only 2 shown, there was an implied hydrogen. That hydrogen did nothing in this reaction. The only thing that happened was that the bond between the oxygen and the carbon broke. Okay? Well, there's electrons in that bond. Where did those electrons go? To the oxygen. How do you know they went to the oxygen? Okay, so pass, that's fine. Pass. How do you know they went to the oxygen?
Carbon had 8 electrons at the beginning and 6 at the end, which means that they had to go to the oxygen since.
If we count out our electrons on our structure to begin with, there were 8 electrons around that carbon. When we go to the product, there are now 6, which means carbon had to lose 2 electrons. Those are the 2 electrons it lost. Okay? That's one analysis. Another analysis, what charge is the carbon here in the product? Positive. What charge was it at the beginning? Neutral. To become positive, what do you have to do? Lose electrons. Where should the arrow go? Away from the carbon. Last one. What can you tell me is the difference between oxygen and carbon? Oxygen is more electronegative. And by being more electronegative, where are the electrons going to go? Towards the oxygen. Okay? Multiple ways we can get at the same, I'm not going to like saying that, but multiple ways to get looking at the same truth. Okay? All of them work. Eventually, things change, and we have to understand each of those ways. At this stage, all we've got to do is look at all the information given to us and just start piecemealing it all out. Make sense? Okay. What reaction happened there? Okay. All we did was break that bond. This is a heterolysis. What's that?
I said the wrong word.
Oh,
I
okay.
meant that.
Okay, we already did the rearrangement. So we move to the last one. What's happening to go from here to here? Okay, we're neutralizing charges. In fact, we're neutralizing 2 charges. How are we neutralizing those charges? I need instructions. What are my instructions? What was that?
The bromine is donating its electrons to the carbon.
I'm taking a pair of electrons from that bromine, which means my arrow starts there. And where do those electrons need to go?
The carbon positive carbon.
To that carbocation. What's the end result?
The bond is formed.
I form a new bond. What happens to the lone pairs around bromine?
One less lone pair.
I have one less lone pair. Why?
Because of those 2 electrons have formed a bond.
Are now in the bond.
That's why your arrow has 2 heads.
That's why my arrow has 2 heads. What happened to the carbon? It was positive and now it is neutral. Why did it become neutral?
So bond has 4 bonds now. Electrons.
We just gained electrons. That's why it became neutral. So we can use the arrow to reference this for us. How else could we reference it? Did we have like a rule at the beginning of the semester for calculating formal charge? Yeah, could we use that rule?
Yes, we could.
Yes, we could. Okay. Carbon has 4 valence minus the number of bonds. 4 minus the number of non-bonding electrons.
0.
And we get
0.
0. So we can use our formal charge rules to calculate those all out, or we can take advantage of knowing what those arrows mean. Those are our instructions. What happened to the bromine?
It became neutral.
It became neutral. Why? What does that arrow show the motion of?
Losing electrons.
Losing electrons. It started negative. It's now lost electrons, so it needs to become more positive. How many electrons did it lose? And that's where it can become a little bit shaky. It's really only losing one. Okay, why is it not losing the second?
Because it's sharing those two electrons in the bond.
It's still sharing it. It still has access to it. Okay? What kind of reaction is that one? This is now just a coordination. Okay? Secret code word?
Red.
Red. Did I write it in purple?
Yeah.
Okay, because there were only two words that were bounced through my head for secret code words. It was red and purple. So I'm hoping I drew it in purple, and that's why it's in my head. Okay, maybe it was a different video. Questions about what you see up there? Okay. That is largely what Chapter 7 is. Here's a reaction. Add arrows. Name the reaction type, okay, or the mechanism type. Okay. That's pretty much the extent of what we're going to do for Chapter 7. So we've now covered an entire chapter in 20 minutes. Okay? And I know you're laughing like, he's not really going to do that. No, that is about it. Okay? Chapter 7 is really just what are these pieces, because now what we'll do is go through and use those pieces and look at the details behind them. Okay? I believe that video started out by also highlighting some reaction types. Okay? So we can now forecast out a little bit. Okay? In that forecast out, what we will be expected to do on this next exam would potentially be something along these lines. Provide a mechanism. What was the mechanism? That was literally what we had just drawn up. Okay? You're responsible for acknowledging why each of those things happened. And plus you're going, oh my God, there's still information I can erase. Provide the product. Okay? There's so many layers behind these. So when we go through and look at these, what you need to be thinking about is not just what's the answer and getting one Y, but get every single one of the Y's that we talk about. Okay? We looked at that individual step and said, well, why did that happen? You said, well, because of this. Why else? Well, because of this. Why else? Because of this. Okay? Why do we need all those freaking Y's? Because I can delete one of the things that's giving you the answer. Okay? So you have to be thinking about each of those individual pieces through this. Believe it or not, you already have all of the tools to do this. Most reactive thing there. Okay, the oxygen. Name this functional group. Alcohol. Name this compound. HBr. Hydrobromic acid. Which is the most reactive thing here?
Hydrobromic acid.
Ooh, it wasn't the alcohol anymore. Why did you say the oxygen?
Because it's the most.
Because our arrow was the one that was reacting. Why is that arrow being used? What's the most reactive thing here? The hydrobromic acid. Which part of the hydrobromic acid is the most reactive? Okay, so we'll do a couple things on this. Let's switch it to something a little bit more familiar. Let's switch it to HCl. Because I heard a couple people go through and say, well, the negative bromine. That's cool. I understand that. Motion of electrons and all that makes sense. Which is the most reactive thing, H plus or Cl minus?
H plus.
Okay. That's a pretty big switch. A lot of you are all just telling me some bromide stuff. Okay. Why now all of a sudden H plus? Because if I go back to bromide now, you're going to be, oh, no, it's the H plus. You're just flip-flopping on your answers. You're not allowed to do that.
It's because H plus doesn't have the electrons and there's two lone pairs on the oxygen.
No.
No.
Size is an important aspect. Why is the chloride not as reactive as the H+?
It's bigger.
It's bigger, so what can it do with that charge? It can distribute it. The more distributed the charge becomes, the more stable it becomes. Okay? There's X amount of insanity. If we put all of that insanity in one person, that one person is really dangerous. If we spread that insanity over a large group of people, hey, it's not quite as bad. Okay? Same thing happens here. Okay? The next part behind this to help with this, because this is a common one that students will mess up on, was hydrochloric acid, okay, or hydrobromic acid, and start referencing the negative species. Have you seen chloride show up somewhere else before? The answer is yes. Like table salt?
Yeah.
Okay. And I know our face burns after a test, but it's not melting off. Is the chloride particularly dangerous? No. And for those of you going, what are you talking about, face burning?
Sweating.
Sweating, that's a nicer way of looking at it. I was thinking more like crying. If you haven't cried yet, the semester's still young. Okay, sorry, it's just, that's OChem. Okay? The chloride's not the dangerous one, it's the hydrogen. Why is the hydrogen dangerous? I like the positive charge, keep working with that angle.
It's attracted to electrons.
It's positive because it is missing electrons. So what could I do to stabilize that? Give it electrons. Where do I have electrons?
Oxygen.
Oh, so I could take electrons like this?
No, we do
Yes.
the other way.
The other way. So I go from the hydrogen
To
to the oxygen. How many electrons does the hydrogen have?
0.
0. Where do the electrons go? From the oxygen to the hydrogen. Exactly like how we drew it before. What would the result of that be?
The big function.
Whoops. Is the oxygen stable with a positive charge? No. So what is it going to want to do?
React.
It's going to react by doing what?
Breaking up
Getting electrons. Where does it have electrons?
the bond to the carbon.
Bonds all the way around it. Could it take the electrons from the hydrogen?
No. That wouldn't do anything. Could it?
Say that again.
That wouldn't do anything?
Can it take it from the hydrogen?
No.
Yes.
It could.
But does that do anything useful for us? No. What does that introduce, though?
A reversible reaction.
A reversible reaction, also known as
I don't know.
152.
I don't know.
Equilibrium. Okay. Most of the reactions we deal with in first semester we keep as unidirectional. We only go left to right. We don't worry about the reverse as much. The reverse is there. You have to watch out for it. Okay. Guess when the reverse reaction shows up a lot? Second semester. Okay. Virtually everything that happens in second semester is going to become problematic because virtually all of them are equilibrium reactions. Okay. Whoops. So if it doesn't get it from the hydrogen, where does it have to get it from? The carbon, which is then going to generate a positive carbon. Is a positive carbon stable? No. So what does it want? Electrons. Where can it get electrons from?
The nearby hydrogen.
The nearby hydrogen. Okay. Why would it do those steps? That one's a harder one because that's pushing at chemistry we haven't quite fleshed out yet. Okay, but do you at least get the point that you have the ability to do these things? Okay? The part that you're missing is someone being pestering and being like, well, did you think about this? Okay? We've already talked about all of these topics. All I'm doing is now asking a question. Okay? And ultimately, the question that I'm asking is an easier question than the one you're faced with. I want you to start asking yourself those questions. Okay? That's what needs to happen. The instant you delete me because you're asking the right questions is good. Okay? Before you get all too depressed or excited about that prospect, okay, we do still have 8 more weeks for me to mess with you. Okay? So, go ahead and clean that all up, and let's move on. predict the products. Right? Label acid base and predict the arrow direction. Okay, let's take a look. Is what I drew valid? Okay. If we go through and add some labels here. Okay, we could even get more funny here. We could call this the conjugate acid. Before you start erasing, stop it. Conjugate base is what I drew here wrong. How many of you drew this? I actually honestly drew it first. Interesting. Most people didn't. Why not? Why did most of you not draw this? Anybody, while I was asking that and making you think, notice what I did?
It's a strong acid.
It's not a strong acid, actually.
Oh, the conjugate acid.
It's actually technically not a strong acid either. It's stronger, but it's not technically one of our strong acids. Why did none of you draw this? What did I change about it? It's the last thing that I added. The arrow. And if we look at that arrow, what am I saying? Goes back to the reactant. Why did you not draw this? Would you draw a product to know that all it does is not form? Okay. This is one of the things that you need to be considering. Okay. Maybe you don't see a product, or you've decided that you're not going to draw a particular product, okay, because you don't think it's going to form. If you don't know that it's going to form, one way or another, what should you do? You should still draw it so you can evaluate it and decide, was your instinct in your brain correct? So how could we look at that and know ahead of time that that reaction wasn't going to happen that way? It's a really hard question, isn't it? One thing that we could go through and do would be to draw out Lewis structures. Because ultimately the Lewis structure is going to help you solve these kind of questions. And of course I drew that one wrong. I'm trying to draw sulfate. So let's draw that one out. SO3 minus 2. Sulfur has what, 6? 24, 26 electrons? Did I do that right?
Yes.
1, 2, 3, 4, 8, 8, 26. And then if we go through and evaluate, that's negative, negative, negative. And we'll have a plus 2, 1. Plus 1 in the middle. So we can fix that. Yeah? Now I can place on my hydrogen. There's my Lewis structure. Okay? Formulas are dangerous things because it hides some of the chemistry. Why does this make the chemistry a little bit more obvious to us? What's the most reactive thing on the left-hand side? What stands out at you of like, oh my God, that's crazy? Here's what I think stands out. You're going to jump in anytime.
That negative oxygen.
That negative oxygen, that negative charge is likely the most reactive thing there. Okay? It is charged. That's going to insanely activate its reactivity. So I want to address something about that negative. Okay? And maybe I want to address it by doing the reaction that I ran here. Maybe not. Right? If I run the reaction that I did here, what's the most reactive thing on the product side?
The nitrogen.
That negative nitrogen. If I take a look at the negative nitrogen versus that negative oxygen, can I use that to help me to predict something about reactivity? Which atom would rather be negative? Why would the oxygen rather be negative?
More electronegative.
It's more electronegative. By being more electronegative, do I want that negative to pick up hydrogen? Because that would then make this nitrogen negative. Is that more stable or less stable?
Less stable.
It's less stable, which means it wouldn't happen. Where's my arrow? Towards the reactants. Did you know the difference between oxygen and nitrogen's electronegativity? Yeah. Did you know you could use that to predict the direction of your reaction?
Yes.
Yeah. One person, yes, the rest of you going, yeah, that's funny. What else could you use? You could use numbers. What the hell are those numbers? pKa's. What does the smaller pKa mean? More acidic. Does my reaction make sense? What did I make the more acidic species do? What did I make the more acidic species do? Act as a base. Does that make sense? No. So why'd you guys draw the other reaction? Because it made more sense. Okay? You have some of that kind of ingrained knowledge in you on how to go through and process these things. Okay? You just don't fully acknowledge it yet. And when we go through and throw structures at you, those structures are enough to break your brain, and all of that ingrained stuff that you picked up in 152 now goes out the door and you lose it. Okay? All I'm asking you to do is keep a hold of that and remember it, because some of that content you can use from 152. Okay? You did a lot of work with numbers and pKa's and being able to predict things. Okay? If you hold on to that, you can use it. Okay? What if you haven't had that content in recent history, or you decided to burn it from your brain? You need some other system. What's that other system? What did we just look at? The electronegativity based off of our structures that we talked about in Unit 1. It stacks. If we have that content from Unit 1, we can use it and apply that content forward. Okay? That's why we talked about it. Okay? So, some acid and base definitions. Okay? Arrhenius came up with some rules that I'm just going to delete altogether because Arrhenius rules are stupid. They're really only useful for 152, and then they just become a waste. The definition that then came out is the Bronsted-Lowry definition, okay, which expanded the use of bases to be outside of hydroxide. Okay, so now what we end up looking at is hydrogen ion donors. Those are acids. Hydrogen ion acceptors are now bases. Okay? That definition, in fact, both of those definitions, need to be locked in your brain because I will explicitly ask the definition. Okay? And if you get it wrong, that's why virtually every other question you get on the exam is also wrong. You have to know those definitions. Okay? It's then a question of applying those definitions out. When we talk about hydrogen ions or H+, we typically refer to them as protons because it makes life easier. Okay? So our Bronsted-Lowry definition of acids and bases, acids are proton donors, bases are proton acceptors. So when I ask for an acid, I'm very specifically referring to the Bronsted-Lowry definition. This is highly different from any other organic chemistry instructor I've ever met. Okay? Typically, when someone talks about the acid or a base, they're referring to the Lewis definition. Okay? I do not use the Lewis definition. Okay? There are some questions that pop up in the smart work, and Cardi will reference the Lewis definition. Okay? It's not wrong, it's just too broad. Okay? So if we went through and looked at these, we should be able to quickly identify these as acids or bases. First one.
Acid.
Next.
Base.
Next.
Acid.
Next.
Base.
I was a little bit slow. Would it help if we drew out the structure? What do you think? Why base? Okay, awesome reference. You saw the spectator ion, and what did you do to that spectator ion? You deleted it. Fantastic. That's an awesome job, which then means you get this. Acid or a base? How do you know it's a base? How can it accept a hydrogen? The negative. Our bases are things that will donate electrons. Okay? So if we can find a source of electrons, we can now find a potential base. Okay? Next one. 5.
Base.
Okay, I'm going to be a bit irritating on this. Right? For those being like, what? Maybe there's the sodium, right? But then what we said, spectator ion.
Neither.
Why are you saying neither?
Because hydrochloric acid is a strong acid that completely disassociates in water.
In both of these cases, if we draw out what happens when they act as a base, what do we generate? This first one is, in the box, name of it. You should be able to name it. It's okay. It's acetic acid. Vinegar. Is that a strong acid? No. So what does that mean?
Equilibrium.
Equilibrium. So yes, the acetate can act as a base because I'm in an equilibrium situation. The next one. If it acts as a base, what does it do? It picks up a hydrogen and we get
Hydrochloric acid.
hydrochloric acid. And what do we know about hydrochloric acid? It's a strong acid. This is not an equilibrium reaction. It favors only that direction, which means, does the chloride ever pick up a hydrogen?
No.
No. So damn it, I can't just say it's negative and it accepts hydrogen? No, you can't. You got to watch out for the strong acids. Okay? CH4. What do you got?
Acid.
Would anybody be happy with a negative carbon? No, why not?
It's very unstable.
Why does it not like a negative charge carbon? Yes.
Because it's higher energy.
Why is it higher in energy?
It's unstable.
Why is it unstable?
It doesn't have
Because
four
there's
bonds.
lots.
I don't quite accept 4 bonds. It does have an octet,
It has a charge.
but I could have the negative chloride.
So that's
I could have the negative oxygen.
it's
Are you
not
talking
that
about
high
carbons
of
that
a
are very electronegative, Adam?
Carbon, in comparison to chlorine and oxygen, is not electronegative, which means it's not going to like the negative charge. It's not pulling the electrons away from the hydrogen, which means I don't generate a positive hydrogen. If there's no positive hydrogen, there's no acid. Okay? So I can fall back on electronegativity to help predict these. CH4 is not an acid or a base. NH3. NH3 is a particularly nasty, tricky one. It sort of can be both. When we look at NH3, we're really only referencing it acting as a base. It has that lone pair of electrons. It can pick up a hydrogen to form ammonium. That is an equilibrium reaction. That's fair game. Okay? Not quite so electronegative that it can't stabilize the positive charge. Okay? Methanol, same kind of deal, but less likely. That oxygen or that functional group with our alcohol can act as both kind of an acid and then a base. Kind of similar to another compound that we're familiar with. Water. Okay? In fact, you will find alcohols act almost identical to water in almost all cases. Okay? So, in our definitions, okay, we've got our Lewis definition, which looks solely at the electrons. is an electron acceptor or an electron donor. If it's an electron acceptor, we can call that a Bronsted-Lowry acid. We could also call it an electrophile. And that's where the problem comes in. The Lewis definition is so broad that it could be applied to virtually every reaction. Well, if it can be applied to every reaction, does that help me classify anything? No. Okay? It's just too insanely broad to deal with. Okay? This is why in this class, when we look at acids and bases, I'm referring to the Bronsted-Lowry definition. It is only the transfer of a proton. Okay? If we look at something that does not involve hydrogen, then we'll refer to it as an electrophile or a nucleophile. Okay? Both of those definitions sit underneath the Lewis definition. It's just trying to come up with a way to be more specific about what's happening. So if we look, for instance, at that first reaction, what changed? What happened?
Hydrogen came off the...
I heard an H3O, so stop right there. You can't contribute anymore. There's a hydrogen. So that has changed. If we compare that structure to that structure, that hydrogen has changed. What else has changed? Circled potentially the wrong one. Okay. Which means the only thing that has happened in the course of this reaction is transfer of a hydrogen. Because it is only the transfer of a hydrogen, also known as a proton, we will now reference this as an acid-base reaction. Okay? If we move to the bottom reaction, so first let's do this. What has happened? What has changed? And sometimes people freak out at this, so we'll draw it up there.
There's no hydrogen.
I'm going to challenge that right out of the gate.
In the reaction.
There's lots of hydrogen, which means there's still lots of hydrogen in the reaction too. What are you going to say? This bromide breaks off. Okay, as a source of electrons somehow comes in. So I'm making and breaking bonds. Are any of those bonds to hydrogen? No. Which then means it's not acids and bases. We're now talking about electrophiles and nucleophiles. Yeah? Make sense?
Yes.
Okay. Since you were good with acids and bases, let's go ahead and label your electrophiles and nucleophiles down here. We've got red and blue. Which one's which? Electrophile, nucleophile? Okay. The red becomes our electrophile, and this is where we should get a little bit more specific. Is the bromine our electrophile? No. What's the electrophile? The carbon's the one that's the electrophile. It's the one that's going to be accepting electrons through this, and where is it getting those electrons from?
The cyanide.
Our nucleophile, or our cyanide, which is going to share electrons in to kick that out. Notice I've now added curved arrows, which means I've now also added instructions for how this happens. Okay? Those instructions make this look like it happens in how many steps? One step. Do those structures make it look like it happens in one step? What does that mean about the arrows I drew?
They are wrong.
They are wrong. We get at the exact same starting point, the exact same ending point, and yet the arrows and instructions I have provided are wrong. I have to be able to look at the structures, both beginning and end, and decide what instructions I should be using to complete that step. Okay? Sounds kind of spooky, but that's what we're looking at. Bless you. Kind of makes sense? Okay. So, arrow summaries. I believe this summary has popped up before. You need to know what each of these arrows means, okay? Because you will be using them a lot. Primarily the curved full-headed arrow and probably also the double-headed arrow for resonance, okay? You need to be super familiar with using those and how to use them, okay? When we look at our curved arrow notations, we're talking about moving electrons. That process of moving electrons in the past has been moving pi electrons. Why could we only, or pi or non-bonding electrons? What were we doing with those electrons? We were drawing resonance. Okay? We were just saying how those electrons could be distributed around the entire molecule. As soon as we now move into this unit, though, what is also happening? What's that? I'm going to argue it's not necessarily atoms that are moving. It's electrons. What electrons are moving that would make it look like atoms are moving? Not non-bonding and not pi, because those were resonance. Sigma bonds. Okay? And by moving a sigma bond, what have I then done to the connection between those atoms? I've broken it. There's our bond breaking. It's not atom movement. It's sigma bonds that are now being allowed to move. When I move those sigma bonds, I get different results. I actually break apart the structure and I change the location of atoms. Because it's not resonance, we haven't talked about it. Now it's reactions. Something has to cause that to happen. Okay? And what looks tricky in a reaction is if we go through and look through these, we could say, well, the atom of hydrogen has changed locations. No, actually it didn't. Okay? Those two molecules have changed locations with respect to each other, but the instant that that hydrogen became connected to that oxygen was not because the hydrogen got close enough to it. Okay? Just because I stand closer to another human being doesn't mean I'm now chemically fused to them. Okay? It doesn't happen that way. Okay? The only reason those two things connect and actually now make a linkage is because the sigma bond has broken. So what we need to be thinking about now is how do I make a sigma bond break? Okay? And a step beyond how is why that sigma bond. So when we go through and look at that top reaction, what sigma bond is breaking? The OH bond. That red sigma bond is what is breaking. Okay? Where would I expect those electrons to go? Why should they go to the oxygen? So I heard two good answers. One, the oxygen is positive. Does oxygen want to be positive? No. So what does it need to do? Gain electrons. So it can steal them from that bond. Okay, why else would oxygen take the electrons from hydrogen? Oxygen is more electronegative than hydrogen. Okay, so we can use those things to help us out. But that's breaking a sigma bond. It just doesn't happen on its own. Something has to cause it to happen. Something needs to come along and help that hydrogen out. Because right now it's just lost electrons. What comes along to help that hydrogen out?
Big structure.
The big structure next to it, I can kind of accept that. Lone pair electrons from the oxygen on that next door structure. So once these two molecules get close enough to each other, they can allow for the electrons to transition. The end result is we get the answer shown. What happens in the bottom circumstance? Broken into two steps. What's the sigma bond? The carbon-bromine bond. Where are those electrons going to go? Why should they go to the bromine?
It's more electronegative.
Bromine is more electronegative than carbon. Fantastic. Okay? But that has to be allowed to happen. In the previous case, it was allowed to happen because the oxygen supplied the electrons. Is there anything stabilizing that carbon, allowing the bromine to leave? So we could say the cyanide, and I like that idea. That negative cyanide is helping it. Is it? Is the negative cyanide causing that carbon-bromine bond to break? No, and we know that because I see that carbocation formed. If the cyanide caused that bond to break, there would be no carbocation. So what allowed that sigma bond to break? What is that resonance doing to the positive charge? It's stabilizing the positive charge. Because that positive charge is now stabilized, bromine can say, peace out, and it can break away from the structure. Only because that other piece has some stability is that sigma bond allowed to break. Okay? So we need to be looking for those aspects and trying to decide what is enough to allow this to happen. At this stage, really early in the game, what is enough going to be? You're kind of going to get told it's enough. How were you told it was enough here? You see the carbocation form. That's how we know it was enough. Something about that carbocation allows this to form. Okay? At the end of this unit, that's when you'll have to be like, I see that structure. I know a carbocation would form. It's allowed to form. At this stage, we're giving you some big hints, guiding you towards that path. Okay? With that, we got to go ahead and stop.